chemistry or quantum mechanics. So far, so we have talked about the proteins and how to calculate or how to simulate protein structures using computers. But from now on, so we're going to talk about quantum chemistry. So, so in order to simulate proteins, we generally approximated atoms as hard spheres, right? But in quantum mechanics, but in quantum chemistry, so we no longer consider atoms as hard spheres, and so instead, so we're gonna solve shredding equations. So the basic of the shredding equation, so the basic of quantum chemistry starts from hydrogen atom. So I think most of you have already learned physical chemistry class 2, right? So I think you already learned. Most of you have already learned about shredding equations. So please try to remind what you have learned in physical chemistry class. So so general shredding equation can be written as like this. So the minus 2m over alpha square and del square psi. Here the psi r is the wave equation, right? So this is the wave equation, and this is the potential energy, a wave equation, and this here, the E is the total energy. So this is very general equation, and as most of you have already learned, and so the del square operator can be written in two ways. So in Cartesian coordinate, so if you write coordinates using x, y, z, then this del square operator is written like dx squared, d squared plus dy squared, d squared plus dz squared, d squared. Or if you use a spherical coordinate, you've already learned, I'm pretty sure that you already know about the spherical coordinate, right? And just at spherical coordinate, in order to specify the location of a point, so this is written with one distance from the origin r, and theta and phi. So the theta means the angle from z axis, and the phi means angle from x axis. So this angle is written as phi, right? So we're not going to go into the details of this theory, but most of you have already learned this from physical chemistry class. So yeah, don't be afraid of this complex equations. So we're not going to solve this, but in principle, so if we solve this, so we can obtain the wave functions. And if you solve this shredding equation on spherical coordinate system, then we can obtain the solutions. So this is the equation, and if we solve the equation, what do we get? So we get solutions, right? So we get solutions, psi. And it turns out that if we solve this equation, then we get solutions, but solutions are determined, or solutions are dependent on three variables. One is written as n, l, m. So you've already also learned about these. And so here the n is generally called as principal quantum number, so in Korean like this. And l is generally written like angular quantum number. And m is generally called magnetic quantum number. So which means that, so if we solve that if we solve the shredding equation, then, so long story short, so this is the shredding equation, and if we solve this, so through a very complex steps, then you don't have to worry about that. And so if we solve this, then so we got the solutions. Solutions are n psi nlm, and these nlm's are integers. integers means, so n is integer large or equal than equal to 1. And what is the condition of L? I mean, L is also known to have value from 0 to n minus 1, and m is known to have values from minus L to L. So which means that we got a set of solutions. So the solutions are written like this, and the solutions are, so the first solution becomes psi 1, 0, 0, and the second solution 2, 0, 0, 2, 1, 0, 2, 1, 1, psi 2, 1, minus 1, and psi 3, 0, 0, and so on. So if we solve this, then we get this set of solutions, and these equations, and these functions, in other words, these functions, if we put these functions into this equation, then so this equation holds. So if we solve that, and many smart people already solved these things, and so if we see the functional form of these solutions, and they are defined like this mathematically. So here the r is the distance from origin, theta, and phi's are defined as spherical coordinates. So, and keep in mind that so these are the solutions of hydrogen atoms. Still, so we're solving hydrogen atoms, and there are many more. And so if n, l, m becomes larger than solution, and functions become a little more complex, but still, we can write down those equations. And then what is this psi? So this is the function. This is the wave function. And then what is the basic postulate? So the postulate means this. So the postulate, or in other words, hypothesis. So the basic postulate of quantum mechanics. So one of the most important basic postulate of quantum mechanics is that if a wave function of a system is known, then the physical properties of the system can be derived from applying an operator to the wave function. So, this sounds a little complicated, but in short, so if we know the wave function, in principle, if we know the wave function of a system, then we know everything about it. So that's the basic theory of quantum mechanics. So as I told you, so these are the solutions. These are the wave functions of hydrogen atom. So since we can calculate the wave function of hydrogen atom, so actually, so we can calculate everything. We can calculate every property of hydrogen atom accurately. So in quantum mechanics, so the how should I say, the holy grail, the goal of quantum mechanics is to obtain, is to calculate the wave function of a system. So let's assume that so we have this kind of molecule. So this is ethane, right? So if we know the exact wave function of ethane, then so we can calculate, so everything. We can calculate, in principle, we can calculate, so what is the homolume gas, or ionization energy, or all kinds of things. So we can just predict only by calculating without doing any experiment. So, but the bottom line is that, so the important part is that, if we know the exact, so the true wave function, then we know everything about the system. But in principle, but unfortunately, we generally, it is impossible to get the exact wave function of a system. So let's look at the one simple example. So let's look at the case of helium. So what is the helium? So helium atomic number of helium is number 2, right? I mean, just so actually, so we can say that it is the smallest multi-electron atom. So I mean, it just has only one more electron than hydrogen. But as soon as we add one additional hydrogen electron here, then Hamiltonian becomes a little more complicated. So before, I mean, when you have only one electron, I mean, so there was nothing like this, and this didn't exist, and also this didn't exist, and so there were only 2 terms. But now we have 5 terms, and also, so what does this mean? So this one corresponds to the kinetic energy. So the you know the kinetic energy, right? So this one corresponds to the kinetic energy of this electron. This one corresponds to kinetic energy of this one, and this one is the potential energy attracted by nucleus, and this one becomes the potential energy attracted by nucleus. And this term is about the repulsion energy, because so this one has negative charge, and they repel each other. So this one corresponds to the repulsion energy because of the presence of 2 electrons. So we only added one more electron, then things got more complicated. I mean before that, so we had only 2 terms, but now we have 5 terms. So the equation becomes much more complex. And actually, people try to solve this, so for a long time, for more than 50 years, but it turns out that it is impossible to solve this, analytically. So analytically means that, so we cannot write down the equation exactly on blackboard, so because it is too complicated, so we just cannot solve that. So it's a bit, weird because, or it's a bit funny because, so we could solve hydrogen atom, but as soon as, we added one more electron, so we can solve hydrogen atoms, but we cannot solve, heliums. So, we cannot solve heliums, so naturally, so we cannot solve, carbons and many other things, and even, and carbon is also, think about it, just one atom, so it's not a molecule. So if things become molecules, and things become much more complex. So in principle, so this is the famous quote from Paul Dirac, who is a legendary physicist who lived in around 1920s and 1930s. And so Paul Dirac said, so the fundamental laws necessary for the mathematical treatment of a large part of physics and the whole of chemistry are thus completely known. So, which is somewhat quite strong statement, but it means that, so in principle, so if we can solve, so if there is a, super smart person, and maybe it could be a god, so if there is a super smart people, then, we can write down the equations based on, quantum mechanics, but we cannot solve this because it's too complicated. So this means that, so the quantum mechanics is very accurate, and so, we know the basic laws of quantum mechanics. So, so in principle, so we have to be able to predict everything about molecule from theory. But in principle, but in reality, the difficulty lies only in the fact that application of these laws leads to equations that are too complex to be solved. So, so we know how to write down the equations. Oh, so we wrote down the equation. Oh, so if we solve this, then we know everything about, molecule, or we know everything about chemistry. But the problem is that this is too complex to solve, so humans cannot solve this. So how can we solve it? So in order to solve this, so we use, in the old days, so people used approximation. So if problem is too complex, then you have to make it simpler. That's what usually, scientists do. So if you see the, physics textbook, so generally, so people, approximate a cow as a sphere, or if there's a person, so we just assume that it is a cubic box or something like that. So if something is too complex, then you have to make it simple. So here, so the first approximation of quantum chemistry is that, so let's assume that, so this is the wave function of a very complex system, and n electrons. So if there are n electrons, so the equation becomes very, very complex. But instead of writing down, considering this directly, so let's just assume that, this complex function will be or must be similar to the product. So the product means that, this phi 1, phi 2, and phi n are multiplied. Multiplied means, right? Yeah. So these are, so this is would be very similar to the multiplications product of these n equations, and each equation only depends on one electron. So which means that this complex one will be very similar to the product of multiplication of simple equations. So in other words, this means that this approximation ignores the correlations between electrons. So which means that, so when you think about this electron, then we just assume that, this one doesn't exist. So, or this one is just, dispersed. So this one is just, dispersed in space. So, so which is somewhat, very strong or very radical approximation, but still works. So when you think about this one, so let's just assume that, so this one doesn't exist. So which makes us a little uncomfortable. So you may think that, that one exists, but we just pretend that one just doesn't exist. But that's a little uncomfortable. But if we don't assume that, so we just cannot solve anything. So that's what usually scientists do. And another approximation, one more approximation of quantum chemistry is that, so when we treat, so like I said, so we can only solve hydrogen atoms. But usually, so in chemistry, so we deal with, so we handle we handle molecules. So what is molecules? Molecules are systems that multiple atoms are connected by covalent bonds, right? So hydrogen atom is very simple system, right? So and we can solve this, but but in real chemistry, in organic chemistry, we mostly focus on carbons and how carbons are connected or disconnected or something like that, right? So actually, so in reality, so we have to, for example, deal with, so this kind of molecules, or we have to deal with this kind of molecules and something like that, right? So they have, they are much, much more complex than hydrogen atom or helium. So, in principle, we cannot solve these. So what do we do? So since we cannot directly obtain the wave function of a benzene, so let's say, for example, let's think about the example of benzene. Then we can write it as a. So we assume that the wave function of benzene can be written with carbon 1 and C2, carbon 2, and C6, carbon 6. So here the C is a coefficient. So let's use A instead of C. A and plus A7, H1, AA, H2, blah blah blah. So since we cannot, it's too complex to write down the wave function of this one. So let's assume that it's just a summation, linear combination. So the linear combination means, so when there are variables, linear combination. combination means you multiply some coefficients or constants and just add or multiply, add or subtract. So this is the general form of linear combination. If you multiply those two, then this is not linear. This is not linear. So anyway, so the basic of quantum calculation is that so we just assume that any orbital, any wave function of a molecule can be written as the linear combination of atomic orbitals. So if we, for example, in the case of water, so water consists of 2 hydrogens and 1 oxygen, right? Then so we have to calculate the wave function of a water molecule, but since it's too complex, so so we just assume that so the wave function of a molecule would be similar to the sum of 1 hydrogen, and 1 oxygen. So if we write down like this, and this wave function and these wave functions are the wave functions of atoms, not molecules. So the right side ones are easier to calculate. So that is the approximation we use in quantum chemistry, and this one, in short, so we call it as a LCAO model. The LCAO model means linear combination of atomic orbitals. So let's take a look at another example. So let's assume that so we are interested in the pi orbital of ethylene. So as you all know, so ethylene looks like this, and this one has a double bond because of 1 sigma bond here and 1 pi bond here, right? So then what is the origin of this pi bond? So this is the pi bond between these two, right? And we know that so based on chemical intuition, we know that this pi bond consists of 2 p orbitals here, right? So we just assume that equation for wave function of this pi orbital, would be the sum of this p orbital and this p orbital. So this is also another example of LCAO approximation. So when we describe this, we just assume that this is this one plus this one. So this is a very simple equation, right? So by doing this, so we can solve this one. So, but so still, so all of these things are approximations. So the approximation, yeah. So they are not true wave functions, and but still we have to use them. To calculate energies and other things. And also, for computational chemistry, so there is also another very important principle called the variation of principle. So I think if you took physical chemistry course, maybe last year or 2 years ago, I talked about this, but if you haven't heard about this, so you can just take a look at the physical chemistry textbook. But anyway, so variational. If we translate it into Korean, then it means it is written like this. Then what is this? Variation of principle. So the variation of principle is a mathematical principle. So in quantum chemistry or in quantum mechanics, here the H is Hamiltonian operator, and here the psi is the true wave function of the ground state of the system. So here the psi, let's assume that this psi is the true wave function. We don't know what it is, but let's assume that this psi is true. Then we can get the true energy of a system, E0, by solving this equation. But as I have mentioned this class, so unfortunately we generally cannot obtain this true wave function. So we use all kinds of approximation. So, but mathematically, so let's assume that so this phi is an approximate wave function. Then, if we calculate the energy by using, this approximate wave function, then, and let's say that, so that energy is written like E here, then mathematically, we can prove that this energy E, this approximate energy, is always larger than true energy. So that is variation of principle. So, the proof of this variation of principle is somewhat complicated, so I'll skip it. But long story short, so if we obtain, approximate energy, then it is always higher than true energy. So that is very, so this behavior makes many things very simple. So in other words, it means that, so if we can make this lower and lower and lower, then the minimum, the lower bound of this value is E0. So, and also, so if this phi, this approximate wave function is very close, is very similar to this true wave function, then energy will be also, this E will be very similar to E0. So because of this variation principle, so we can, measure, or so we can just, assume, how we can, estimate, we can calculate the accuracy of our approximate wave function. So this is called variation principle. So, so this is one of the most important principles. So based on these, based on this variation principle and approximations we talked about, then so we can calculate, we can actually do quantum calculations. We can make computers to solve, complex, quantum mechanical equations. So one of the most famous quantum mechanical program is Gaussian. So this is the most famous, quantum chemical package. But there are other packages like games or QChem or some other packages. But this one is the most widely used one. So during the practice session, so we're gonna learn. We're gonna run some example, tasks of Gaussian jobs. Then let's briefly take a look at what Gaussian can do. So Gaussian can do in general about 1, 2, 3, 4, 5 things. So the first, you can do single point energy calculation. So single point energy calculation means, so the single point means that just it uses one structure. So if we give a computer a structure, then it just calculates its energy. So it doesn't consider whether the input structure is good or bad. It just calculates the energy. So that's single point energy. So this is the simplest task. And second thing is geometry optimization. So the geometry is, in other words, structure. So the structure of molecule is optimized. So optimized means so when you have if your structure had, let's say that so this here the y-axis corresponds to the energy of a molecule, then let's assume that so your molecule is here. Then if we do optimization, then we know that the molecule becomes stable. Molecule becomes stable when this molecule has this structure. So by lowering its energy, so optimizing means minimizing, lowering the energy of a molecule is a geometry optimization. So this calculation, fix some bad structures. So let's say that so your input structure has some bad clashes, static hindrances or some static clashes, then so geometry optimization will solve that. So for example, if two atoms are too close, then it should repel a little bit. Or if two molecules are too far away, then they should be attracted a little bit or something like that. And also, so Gaussian can calculate vibration frequencies. Molecules actually, so as you have already learned from physical chemistry class, so molecules are vibrating at room temperature. At 300 Kelvin, so things keep moving, and so generally, if we think about the carbon dioxide, then it vibrates like this, or it vibrates like this, or it vibrates like this, and it keeps vibrating. So the Gaussian can calculate, how molecules will vibrate, and what kind of, how much energy will it, observe or something like that. So we can predict IR, Raman, UV, NMR spectrum, so without doing experiment. So you can compare, experiment and theoretical calculations and something like that. And also Gaussian can predict transition states or can calculate reaction paths. But these things are a little more complicated, so we're not going to do this on this term. And okay, so let's see. Okay, so so for the Gaussian calculations, for quantum mechanical calculations, so you will see the word called basis set. So the basis sets are, so as I described, as I mentioned in this class, so usually, so since we cannot calculate the true wave function of a system, so we have to approximate it as a sum of some easier ones or things we know. So let's assume that so this is the true wave function of a system, but since we don't know, so we'll express it. We'll write it as a sum of chi1, chi2, chi3, and chi4. And chi functions here, the chi functions are called basis functions. And these chi functions are, of course, so the functions that we know. So we know chi functions, but we don't know this one. So we approximate this one using chi functions. And so let's assume that so here, so this is the example. This is one example. Let's assume that so this red line is the true s orbital. So we like to calculate this s orbital. But since but let's assume that we don't know this red line, the equation of this red line. Instead, so we approximate it using this blue line, and this blue line has a form of Gaussian function. So the Gaussian function means actually the name of the software also comes from the Gaussian. So the Gaussian means a exponential minus alpha x squared. So this form of function is generally called Gaussian function. So here this blue line is a Gaussian function, and they are similar, right? So this blue line can be a good approximation of this red line, but if we add three more lines, this blue, green, and yellow lines to this blue line, these three Gaussians, then some of these three lines becomes this blue line. So if you see, if you see this line, actually this blue line, is overlapped with this red line. So you cannot see blue line here, but so it deviates here. It deviates at the end of the graph. So if you see this graph, then we can see that some of these three Gaussians are better than this one Gaussian. So if we add many functions here, then we can approximate this wave function quite accurately. So that is the basic concept of basis set. And while doing, Gaussian calculations, you will see, keywords like this, 321G or 631G or 6311G dp or something like this, and so they sounds very like, passwords or very complex words, but I mean, they have some kind of meaning, so I'll talk about it soon. So in quantum chemistry also, generally there are two types of basis sets. So the one is Slater type orbital. So the Slater type orbital means that so the orbitals are approximated by the sum of this function. So this is Slater type functions are exponential minus alpha r. And Gaussian types are alpha r squared. So that is the only difference. So if you write down if you plot the shape of the function, so the exponential minus alpha r looks like this, and exponential minus alpha r squared looks like this. They look similar, but a little slightly different, right? And this is here, the dotted lines are Gaussian functions, and solid line is a Slater type orbital. So so they are similar, but a little different. So the advantage of Slater type orbital is that they are good for describing the tail part of orbitals. So they are a little more accurate than this Gaussian type orbitals. But the disadvantage is that they are expensive. So the computers don't like to calculate, do this calculation. So this is the exponential minus alpha is a little expensive. But for Gaussian type orbitals, so I also don't know why, but so this kind of Gaussian type calculations are faster than doing this calculation using computers. So in order to understand why, so maybe we should ask Intel, but I don't know. So anyway, so calculating this function is much faster than calculating this function using computer. So these days, people generally mostly use this Gaussian type orbital to do quantum chemistry. So here, so you will see, so this kind of keywords very frequently, and so let's say, let's look at, what does that mean? So here, let's assume that, there's a 321G keyword. So the 321G keyword means that so when we do, quantum calculations actually using Gaussian or other quantum packages, so we divide the whole orbital into two. So this is the this is the p orbital. So this is the p orbital. Then we can divide it into inner part and outer part. So inner part is described by the sum of 3 Gaussians. So this is the inner part. And also here the 21G means, so this outer part is described by 2 Gaussians and plus another Gaussian. And here the G means, so we are using Gaussian type orbital. And here in this example, let's just, if we use 631G basis set, then so this bright side is described by 6 Gaussian functions, and this outer side, this outer part is described by 3 Gaussian function plus, 1 additional Gaussian function. So we can easily think that so 631G will be more accurate than 321G. So as we have seen before, so more Gaussians are more accurate, right? But if we use more and more functions, then things becomes more and more complex, and calculations becomes more and more expensive. So there is always good side and downside. So which means that so this is the example. Let's assume that so we calculated the wave function of an atom, some random atom. Then we can get the coefficient, we can get the numbers. And so here in this example, so this 1s orbital is approximated by sum of 4 Gaussians, right? So this is Gaussian 1, 2, 3, 4. So as you can see, so here the exponential minus whatever number and r square 4. So this is the sum of 4 Gaussian. So in quantum chemistry, so when we say so we obtain the orbital, means that so we write the wave function like this. So this is not total super 100% accurate, but they are approximations. So the key is how to tune these numbers. So if we get accurate numbers, then we get accurate results. So this is the practice of quantum chemistry. And so usually, so 631G basis set is enough. But sometimes, so if you, maybe some of you will go to, grad school, and then some of you may have to read some, papers. Right? So if you read, sometimes if you read some organic chemistry papers or other papers, so which use, quantum calculations, then you'll see something like this, 631G star or 631G plus star star or something like that. So here the star means, so when you see only one star means it will consider polarization. So the polarization is you know what is polarization, right? So the polarization means when there is an orbital. So if something negative comes to here, then this side becomes slightly positive and this side becomes slightly negative, right? And this kind of polarization, so this is the polarization, but and this kind of polarization effect is more important in heavy atoms, like transition metals. So one star means, so we're going to consider d orbital for heavy atoms. So usually, so we don't consider about d orbitals, right? So if your system only consists of carbon and hydrogen, so usually d orbitals are not important. But if you deal with metals, d orbitals are important for metals, right? So in order to calculate the properties of metal ions, then you have to put one star. And there's also another star. So sometimes you see two stars. One additional star means, so we are going to also consider polarization of hydrogen by considering p orbitals. So what this means? So generally, hydrogen atoms are drawn like this, right? So hydrogen atoms, electron of hydrogen atom usually stays at 1s orbital. But sometimes, in principle, hydrogen atom also has p orbitals, right? But they are empty. So because so if you give them energy, then this electron can jump to p orbital. So in general, so we don't have to consider the p orbitals of hydrogen, but sometimes you have to consider, so p orbitals of hydrogen during calculation. When? When hydrogen bonds are important. When if CH bond is broken or formed. So then this kind of polarization is important. Also, sometimes you see this plus signs. So the plus signs means diffuse phase function. So the diffusion means something is spread. So here the diffusion means electron diffusion. So the electron diffusion means so the electron diffusion means so when you have a nucleus here and electrons are here, actually So the probability of an electron decreases as distance goes, right? So usually, so we're gonna just, consider until here. Let's assume that the probability of electrons staying here is about 99.9%. Then, I think we're enough up to here. So let's just assume that there's no electron, outside of the atom. But diffusion means that so we will consider longer regions. So we'll consider we'll assume that electron can go very far. So electron can spread very far away. So this kind of diffusion functions are sometimes important, sometimes not important. But usually so this kind of diffusion functions are important when your atom is very large and when your atom is an ion. Because anions have more electrons, right? So anions have more electrons than usual. So so their electrons are more spread out. So you have to take into account the diffusion. So yeah, so these things sound. I know that these things sounds very complex and maybe too hard, but actually running Gaussian is much easier than running proteins. So you'll see.